So when we did optimization before, we have done this with quadratics. We used our calculator to find the max and min of a quadratic. Maximization, minimization. We also did it with cubic functions, where cubic functions didn't necessarily have a max, but what cubic functions did have was something called, anyone remember what this spot was called? The local maximum, yes. And that's what we're going to have for rational functions as well. Rational functions might not have a maximum, because remember they do kind of go up forever on one branch, but they will have a local max that we'll be trying to find. All right, looking at our first one, talking about medication when it gets administered at a hospital. A certain drug is injected into a patient, and the concentration, I need a highlighter because I see a variable there, the concentration C of the drug in the bloodstream is monitored. At time of t equals 0, or excuse me, t is greater than 0, in minutes since the injection, the concentration in milligrams per liter is given by this function here. C of t, which just means, concentration equals 15t over t cubed plus 12. Notice they said t has to be greater than or equal to 0, which basically means we're working in quadrant 1, because we don't want negative time, and we also don't want negative drug concentration in the patient's bloodstream. So that's going to help me figure out what my window of my calculator needs to be as well. So let's go ahead and grab our calculator. First thing we probably want to do is just clear the memory. Algebra 1's been using these a lot, so who knows what they have typed in. How do we clear the memory again? Second, and then the plus sign, and then we type 712. Okay. And then to graph, where are we going to go? Y equals on the top left. Good. Now, we don't need to type the C of t part of it. We only need to type the right side of the equation. And notice we do need a fraction. There's two ways to get a fraction on y'all's yellow calculators. You can press alpha and then the button right next to it, the xt theta n button. You can press alpha and that. Hey, Leela, we're calculating. My calculator's old, so I have to press alpha, y equals, and then press the first option. Yeah, that works always, yeah. And then on the numerator, what do I need to type? 15t, 15, and then my calculator's not going to give me a t when I press the variable button. It's going to put an x, but does that matter? No, that does not matter. Underneath that, we need an x to the third power plus 12 to the third power plus 12. If you have trouble getting an exponent, talk to someone in your group. Honor, follow along, hon. This is important. Did you grab a calculator? Are you following? Thank you. Okay, when we graph this, it's not going to look great. We're going to have to adjust the window a whole lot. Yeah, it probably just looks like a regular rational function. Okay, everybody got it typed? Everybody got it typed? Okay, pressing graph. There you go. That's a rational function, right? That's what it should normally look like. But we don't need quadrant 2, 3, and 4. So we're going to go to our window. Window. Very good. The x minimum, we don't need any negative numbers on our x-axis. So I'm going to make that 0. Do I need any negative numbers on my y-axis? No, so I'm going to make my y minimum 0. Okay, and again, that still might not be great, but we can press graph. We change the x min to 0 and the y min to 0. Everybody change those? Let's graph and see if we need to adjust more. Okay, that's not bad. Technically, you might be seeing a whole lot more of the y-axis than you need. Like, you might not need to see all 10 numbers on the y-axis. I'm going to make the window for my y maximum, I'm going to make that a 5 instead of a 10. Because I probably don't need to see up to 10. So now if I press graph, I change my y max to 5. Very nice. I'm going to draw this on my paper. I'll give it a little doodle over here. What was on the x-axis? What piece of information is x? X is time. Yes. Good. What information is on my y-axis? The concentration in milligrams per liter. Concentrate. How do I spell concentrate? T-I-O-N? In milligrams per liter. Okay. Alright, we've got that. I'm going to graph it. It has a little up here, and then it flattens out again. So, question A says, what is the highest concentration of the drug that is reached in the patient's bloodstream when the time is greater than or equal to 0? Do y'all see on this graph where that highest concentration is going to be? It's going to be right here at the peak. This is where the highest concentration is. This is what we need to find. That's what's called our little local max. We're going to go find that local max. That is where our highest concentration is. Okay, so back to my calculator. Do we remember the steps for finding that? Second. Second trace, which pulls up the calculate menu. I'm going to write down those steps over here. We press second. We press the trace button. That pulls up the calculate menu, and we select which option? 4, the maximum, yep. Okay. And then it asks you 2 questions. First question is left bound, which means you want to put your little cursor somewhere to the left of where you think that peak is. Somewhere to the left. There we go. I think that's to the left of it. And then you're going to press enter. And then the second question is right bound, so put it on the right of where the peak is. Press enter. And then the last thing is guess, which means you want to actually press enter for the last time. And it tells us the maximum. How many places y'all want to round to? Hundreds, 2 places? Okay. So my first number would be 1.82, because that 7 is going to bump the 1 up to a 2. And then my y value would be what? 1.51. Okay, so to answer their question, the question says, what is the highest concentration of drug that's reached in the patient's bloodstream? I don't want to write this ordered pair. I want to decide which one of this ordered pair is my answer. Is it, remember, what does the X value stand for? The time. This is time. The second one is your concentration. So what answer am I writing? 1.51. 1.51 milligrams per liter. What happens to the concentration of a drug after a long period of time? It keeps going down. Eventually it starts going down to 0. But technically we probably know that there's an asymptote. Actually, no, the asymptote would be here on bottom. Yeah, the asymptote is at 0 because it's here on bottom. So it just eventually goes down, 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 down. It gets closer to 0. Let's write that. Eventually, or it's lowering towards 0. What'd you say, Mason? Becomes part of your DNA. Yeah, it's probably just a representation. Not too bad? Alright, let's look at our second one. Everybody ready for second one? We're done with our doodles. Rare species of insect was discovered in the Amazon rainforest. To protect the species, environmentalists declared the insect endangered and transplant the insects into a protected area. The population of the insect T months after being transplanted is given by this function, P of T, where P stands for population. 50 times the quantity of 1.05 T over 2 plus 0.01 T. Alright, so our first question says how many insects were discovered. In other words, what was the population at T equals 0? We we can actually do this by hand. We don't need a calculator for that. How do we find population at t equals 0? Yeah, plug in 0. Plug in t equals 0. So we would get 50 times 1 plus 0.5 times 0 over 2 plus 0.01 times 0. So the numerator, we would get, simplify 0.5 times 0 would become, and then if I add 1, I get 1. And then if I multiply by 50, I get 50. The denominator, 0 plus 2, would become 2. So what was the population of those insects at time of 0? 25. Wow, they really are endangered. 25 insects. Okay. Determine the horizontal asymptote of the function. And then what is the largest population that the protected area can sustain? To find the horizontal asymptote, we might want to actually maybe, do we need to, yeah, we might want to FOIL it out just to see, actually, first of all, degrees. We'll start with degrees. Is the degree bigger on top or bigger on bottom, or are the degrees the same? Yeah, the degrees are the same. So remember our Bobo-Blatt's ECC? If exponents are the same, how do we find the horizontal asymptote? Yeah, we'll divide our leading coefficients. It's a little hard to see the leading coefficients when it's in this form right here. So that's where I said I think I'm going to distribute it out so I can easier see my leading coefficients. On the numerator, if I FOIL out, I'm going to have 50 plus 50 times 0.5, which would be 25t. Okay, and then on the bottom, I've got 2 plus 0.01t. Technically, if we write that in the proper form, it would be 25t plus 50 over 0.01t plus 2. So to find my horizontal asymptote, I'm going to need the ratio of those two leading coefficients, which would be what number over what number? 25 over 0.01. So my horizontal asymptote is going to be at 2,500. Wow, pretty big. Okay, that might help me think about what my window is going to need to be whenever I graph this, and I probably see a terrible graph.
It's going to be like 100.
Okay. All right. So going to graph it now. I'm going to grab my graphing calculator. I'm going to go to y equals, delete out my old function. You can either type this one with all the parentheses, or you can type the one that we FOILed out. Either way, it should be the same. But I will need a little fraction in there. On the numerator, I'll have 25t plus 50. Honor, lift your head. Thank you. On the denominator, I'll have 0.01t plus 2. I'm just typing in the one that's been FOILed out. And again, when we graph this, it's not going to look good because we have the old window. And it probably does, with a horizontal asymptote of 2,500, we are probably going to have to adjust our window. So I'm going to go to graph, see how bad it is. Yeah, it doesn't even show. Alright. I'm going to press zoom standard so I can just go back to my regular window. Okay, well, there's a little something there on the regular window. So I press zoom and then option 6, which is the standard window for that. Alright, so going to my window now to adjust it. Again, I don't need any of quadrant 2, 3, or 4. I only need quadrant 1. So I'm going to turn my x-min to 0 because I don't need any negative x's. I'm going to turn my y-min to 0 because I don't need any negative y's. And then now we need to think about how big the x-max and the y-max should be. 10,000? Did you already do it and it worked? Dang, y'all are ahead of the game. What about the y-max? 10,000. Alright, everybody adjust your windows, typing it in our numbers so we all have the same.
It kind of just looks like
Okay, I'm a graph. Okay, alright. That's not bad. Okay, I'm gonna give this one a little doodle. Here's my time in months. What's on my y-axis? The population of insects. Let's graph it. It goes up and then it flattens out. What number is this that it's flattening out at? 2,500, right. This should be your horizontal asymptote. Okay. Spoiler alert, we already know the answer. What is the largest population that the protected area can sustain? Anything less than 2,500. Yeah. Anything less than 2,500. Any number less than 2,500. Because the max is 2,500. Good job on finding the good window for that one, guys. Alright. One last one. We've had these steps before. Yes, we've had I promise you, if you go back and look at notes, all the notes we've done on optimization, we've had these before. I literally copied these from a notes that we've had before. Okay, CVHS Investing Club. They got into the soup business. They're banking on this being a big year for soup. Standard can of soup is 12 ounces. 12 ounces is 355 milliliters. The process of manufacturing is expensive, both from a financial perspective and an environmental perspective. The Investing Club wants to find the dimensions of the 355 milliliter can that minimizes the can surface area. This means that we need to find the ideal radius and height so that we can determine what size can will use the least amount of metal but still hold 355 milliliters. Because this is its volume. Okay, its volume is 355 milliliters, 12 ounces. But we want to see how can we adjust this can so that we still have the right amount of volume, but we want to use the least amount of surface area metal. Therefore, like, it basically makes our costs less. For the volume, again, the 355 milliliters, that's our volume. Okay. Let's see. Draw a picture of the situation and label the variables. All right, we've got ourselves a can, which is a cylinder. What are my two variables? Radius and height. Here's the height. Radius, remember, is from the center and just halfway out, not all the way across. What's all the way across called? Diameter. Good. Okay. Write an equation for the quantity you wish to optimize. Now, technically, we're not maximizing anything. We are minimizing. That is the quantity we want to optimize. So we are trying to minimize what? Are we minimizing the volume or minimizing the surface area, according to the question? Yes, we want to minimize the surface area. Okay. Surface area is which of these two formulas? The top one. Okay, so S equals 2 pi r 8, 2 pi h squared. There's no height in it. 2 pi r squared plus 2 pi r h. The reason, have y'all ever learned why it's this formula? I know it looks like weird, but this is basically the two circular bottoms, and this is like the area area of the square. It's actually maybe not a square, a rectangle in the middle is this back one here. All right, write any constraint equations. The constraint equation is what we have to stay within, and that's going to be the volume. We want to make sure we have a certain volume. So my constraint equation is my volume, and that equals pi r squared h. What do we want that volume to be? It has to be, we were told in the question, 355 milliliters, yeah. 355 equals pi r squared h. Okay, all right, we get it. Substitute the constraint equation into the optimized equation so that everything is in terms of one variable. So when we look at this, okay, which variable would be easy? If I need to take this one and substitute it in, which variable would be easy to isolate? H. Yeah, H would be easy to isolate. So if I have 355 equals pi r squared h, I want to isolate the h so that I can substitute it. How do we isolate h on this one? Divide by pi r squared. Yep. Pi r squared. So these are going to cancel, these are going to cancel, and I'm going to get h equals 355 over pi r squared. Okay, so this says to take that and substitute it into my optimized equation. So in this optimized equation, we're going to take that h and put it where? Yeah, in place of the h. Yeah. So I'll have, let's see, s equals 2 pi r squared. No h on that part. Plus 2 pi r, and then in place of that h, we're going to put 355 over pi r squared. Good. Okay. Let's try and simplify what we can. This is multiplying, so things can cancel diagonally when you're multiplying. What can cancel? A pi can cancel, and what else? An r can cancel. So how many r's will we still have on the denominator? 1. So I'm going to have 2 pi r squared plus, now this says 2 times 355 over r. Okay, so we'll get s equals 2 pi r squared plus, what was it, Danny? 710 over r. So now we have an equation that's just in terms of one variable now, so we don't have two variables anymore. We just have an r. Okay, did that. Now we're going to determine the maximum or minimum value within the correct domain, but are we trying to find maximum or are we trying to find minimum? Minimum. Okay, within the correct domain means we don't need quadrant 2, 3, or 4. We only need quadrant 1 because we don't need a negative radius. We don't need a negative surface area. So I know it's negative, or I know it's just quadrant 1. What is my input variable that's on my x-axis? The r, yeah, the r. This is actually a radius. And then what is my input or my output variable that's on my y-axis? Surface area. Surface area. And again, we're trying to find the minimum value for this one when we graph it. I'm going to go to my y equals screen. Honor. Honor! I already said. Thank you. You need to go get water? Go. Alright. Do you know where the pi button is? There's a little one in blue right here. There's one. 2 pi, and then we need our variable squared plus 710 over r. 710 over r, which is technically just x. Oh, there we go. This might not look good because it has our old window on it. So when you graph it, it might be terrible, and we might have to adjust our window. Does y'all look like that?
Mine is, I
Press enter again.
Wait, enter stops it for your
Mm-hmm.
Wait, why does it?
Stop pressing enter. If you press enter again, it'll pause. But if you press it again, it'll unpause it.
This one too.
Okay. So let's go to our window. We wouldn't need to lower the X max and the Y max. Yeah, I'm going to go back to 10 and just see what that does. Okay, well, I see nothing. We need to make our Y max probably bigger. What do we want to change it to? 1,000, 100, 500, 2,000. Amari did. Oh, yeah, that looks good, Amari. That's good. Huh? We did 2,000. Okay, I'm going to graph that over here. Let's see. It comes up this, comes from this way. It goes here, goes that way. And we're trying to find which part of this graph? The minimum. So we need to find down here. I know. Okay. Let's see. My minimum. Second trace. Nope, I did not press second. I pressed alpha. Second trace. And then? Which option? 3. Cole, you already answered the question? You're just not following along? Left bound. We need to put that somewhere to the left of where we think the bottom is. I hate how it writes over my graph, so I can't even see the graph. Okay, press enter. Right bound, put it somewhere to the right of where you think the bottom is. I'm just guessing. And then press enter. And then one more guess, and it should give us a point at where it thinks the lowest point is. Did y'all get this?
To be honest, at first I did like entirely wrong because I put 2 pi r squared times.
Oh, instead of plus?
Yeah. Plus, and so I was like, wait, what? Because it was a linear function. So, and then I was like, oh, okay, and I changed it. But then I accidentally put plus inside of it, like, plus so then it came out as a quadratic function. What's going on?
All right, let's write down our minimum rounded to 2 decimal places. My first number would be 3.84. Very good. Okay, and my second one would be 277.55. Very nice. And then we just need to make sure we answer the original question. Just because we found the minimum doesn't mean we answered the question. The question actually said, let's go back and read it. Find the ideal radius and height. Find the ideal radius and height. Are one of these the radius? Yes, one of these is the radius. Which one is the radius? 3.84. Radius is 3.84. Okay. Height. Oh, we have a way to find height. No, look right here. 355 divided by pi times our radius squared. So our ideal radius, and then our ideal height, we're going to need to substitute. It does look wrong, yeah. Find the ideal height by substituting. Okay, so let's see. We will have h equals 355 over pi r squared. We'll substitute in our r. 3.84 squared What was it, Mason? 7.66. All right. What should be our unit on these?
Centimeters. No,
Well, milliliters is not a measure of radius or height.
oh,
Why is it centimeters? It is centimeters.
I say centimeters.
Say it again. But do you know why, Danny? Do you know why it's centimeters?
Since measuring system.
Yes, because milliliters is technically centimeters cubed. So if those are my centimeters cubed, then my radius and height should be centimeters. Yes, they kind of. Did y'all learn that in chemistry? Where do you learn that? Nowhere. Everywhere.